All right, so let's do this in 2 steps. We already know how to do gradient descent for a linear unit. Okay, so the first step is figuring out how to do it for a single sigmoid unit. So this is still just one perceptron, except that it's a perceptron that now has the sigmoid instead of having nothing. Okay, and then at that point we are finally ready for backprop. We're going to see how we do this on networks with many layers of neurons. Right? So one way to look at this is after we've done this part, we will know what the derivative of the error is with respect to a weight at the output unit, right? Because if you take the hidden layer as fixed, right, finally you just have output units, and at this point we will know how to do things for those. But then that really interesting problem comes: what is the derivative of the error with respect to the weights in the hidden units, right? Because that error, is passing through the units that are not hidden. And by the way, we're going to do this, with one hidden layer in mind because that's what people use 99% of the time. But in principle, this could apply to any number of layers. Okay. All right, so let's do it. Any questions so far?
Just about what you just said. Is there ever a reason to have multiple layers in units?
Wonderful question. And the reason is, the answer is absolutely yes. Networks with more more layers are much more powerful than networks with fewer layers. In the following sense. So we will see later when we talk about the representational power of the perceptron that actually, if you give me if your function is always finite, and actually let's just take the Boolean case, simplest case. You can here's an exercise to the reader. Figure out how to represent any Boolean function using a neural network with only 2 layers. Can you think of how to do that? There's actually a very simple answer, right? And I'll even give you a hint. First, convert your function to CNF or DNF. Okay, pick one. Let's say we pick DNF. Okay, so now your function is in DNF, right? How do you represent this using a neural network with 2 layers?
A layer for AND, a layer for OR.
Yeah, right. Remember, we saw last time how you can represent an AND using a single perceptron and how you can represent an OR, right? So what do we have with DNF as well? I need a neuron for each of the ANDs, right? And then I need a neuron for the big OR, and we're done. So, by this time you might think, well, what is the point of having more layers, right? I already have everything I need. Well, here's the key difference, is that functions that take an exponential number of neurons with 2 layers might take only a linear number of units with more layers. In fact, our good old friend or our good old enemy, the parity function, if the number of layers that you have is even 1 minus the number of inputs, you need an exponential number. But if the number of layers is equal to the number of inputs, then you only need the linear number. I will leave this as an exercise, right? You might actually sort of already have an inkling of where this is going to come out. But look at the difference, right? By having very deep networks, I actually took the complexity of representing my function that I want to learn from exponential to linear. And of course, it's not just the complexity of representing it, it's the time to compute with it, and it's having samples to learn and whatnot. Okay? So in general, having deeper networks is a very desirable thing to have. Also, look at your brain, right? If your brain was just 1 layer, you wouldn't be taking this class, right? Even the flatworm has more than 1 layer, right? There's nature, doesn't do anything with networks with just 1 layer. Okay? In fairness, networks with 1 layer, as I mentioned before, can be used for lots of things like, predicting stock fluctuations and foreign exchange and things like that. But, definitely networks with more than 1 hidden layer are more powerful. Okay? Other questions? Okay, so let's do this. So let's repeat the thing that we did before for the linear unit, but with our new nonlinearity added, right? And let's see what changes. It's actually not that much, okay? So remember, I want to compute the derivative of the error with respect to each of the weights, right? We have a single neuron, it has a sigmoid at the output, okay? So here's the same thing as before. The derivative of the sum is the sum of the derivatives. So far, so good. And now I apply my chain rule, right? And here I have it, right? It's 2 times blah times the derivative of blah. And these guys cancel, same thing as before, right? But now let's get to, the more interesting part, okay? So remember, dwy of td minus od, right? This part goes away, right? Because t is the target value, it's a constant, right? But now what I have is the derivative of the output with respect to the weight, right? Before this was easy, right? It was just the corresponding feature because it was a linear function, right? But now there's a sigmoid there in the middle, okay? So what I actually have is a composition of two functions, right? The linear sum, right? And the sigmoid, so I can apply the chain rule, right? Backprop is all about the chain rule, really, right? So I can decompose my derivative of the output with respect to the weight into a product of two things. The derivative of the output with respect to net, remember net was what I called the weighted sum, times the derivative of net with respect to the weight. Right, everybody agree? Okay, very good. And now we're almost done actually. Right, because we know that the derivative of the output with respect to net is just the derivative of the sigmoid, right? Which is O times 1 minus O, right? So this is just the derivative of the sigmoid. And the other one, of course, is just the linear, the derivative of the linear function, which is just, xid. Right? So d is the data point and I is the feature. Okay? So now all we have is the product of these two things. Right? So bottom line, what is my new derivative compared to what I had when I just had the linear unit? It's exactly the same thing, except that there's now this additional factor of OD times 1 minus D, and that is just the derivative of the sigmoid. Okay? No big deal. Right? Any questions? Right? So far, so good. Now, let's do a clever little trick. We're going to call delta K minus the partial derivative of the error with respect to net K. Why am I doing this? Because this is actually the error signal that we're going to backpropagate. What we're going to compute is successive of these derivatives going backward from the output. In fact, that's why this is called backpropagation, because what I'm going to do is, when I'm given a new example, first I propagate it forward through the network to the output, and then I compute the derivative of the error at the output, and then I backpropagate it one layer and two layers and as many layers as I need to. And the thing that I'm going to be backpropagating is the delta K's. So what I'm going to get, to do backprop is a function for the delta K's in one layer. Sorry, is an expression for the delta K's in one layer as a function for the delta K's in the higher layer. Okay, so the ones at the output, we already know how to compute, right? Those are just, plain units, sigmoids, right, that we just saw how to do. And then from those, we compute the first deltas, right? And then from the deltas, we compute the deltas for the back until we've gone through all the layers, right? And in a narrow, with just one hidden layer, which is what, people typically use, I just have to do that once, actually. Okay? So, calling this delta K, let's see what delta E with respect to net J is for a neuron, right, that's in the hidden layer. Okay, so this looks like a bunch of ugly math, but as you'll see, it's fairly straightforward. And this is really where the action of the backpropagation algorithm is, right? We are now ready to compute the derivative of the error with respect to a weight of a hidden unit. So, going back to this figure, right, we already know how to compute the derivative of the error with respect to these weights, right? The weights of the output units. Okay? And notice that in general, in this case, and in the car driving case and whatnot, there's multiple output units, right? So my total error is going to be the sum of the errors for each of the units, right? How many errors am I making on, what is my error on head plus what's my error on head, and so on and so forth. Okay? So we already know how to compute the derivative with respect to these units because they're just sigma units at the output, right? Easy street. What we're going to do now that's new, and it's the trickiest part of all of this, is computing the derivative with respect to these weights, right? The weights of the inputs in the hidden units that are one step removed from the output, and the fact that they're one step removed is what makes things complicated. Okay? So this is what we're going to do now. So how are we going to do this? Mm-hmm.
In the delta K, what is K? K is the number of the kth output unit, or
it's the number of the unit.
just
So for each unit, we're going to have K, we're going to have a delta K. I mean, more general, think of this as the following: units are indexed by whatever, right? By the layer and by the unit, right? And we're going to have a delta with exactly the same indices. Actually, sorry, yeah. This is going to be for each weight. You'll see shortly, right? So yeah. Okay, so how are we going to do this? I want to compute the derivative of the error at the output with respect to this guy, right? Step 1, sum rule, right? Sum rule just says that the derivative of a sum is the sum of the derivatives, right? So the derivative of the total weight with respect to this guy is, first of all, it's going to be a sum of the derivatives of the errors of each one of these. You agree? Right? Naturally, right? That didn't arise, with these units because, at the output units, only one output depended on each of the weights, right? So there was no question of summing over all of them, right? The error with this guy, for example, the error here does not depend on this weight, right? So there was no sum rule to apply there. But now, the error is going to depend on this guy. This is the first key idea, through this guy, and this guy, and this guy, and this guy. You see? So what are these guys? These are the weights from this unit to all the output units. Okay? So I'm going to need to sum over those. Step 1. Okay? Everybody got this? This is the first key idea, right? This guy has an effect on the output error through each one of these. Okay? Sum rule. Second step, of course, is the chain rule, right? Now we have a sum over these paths, right? One path, two paths, etc. In each of those paths, now I'm going to apply the chain rule. But now this is a much more complicated application of the chain rule because notice what's going through this chain, right? There's the sigmoid at the output. And then there's the weight from the hidden unit to the output. And then there's the sigmoid of the hidden unit. And then there's the weight going into the hidden unit, right? And this is what, can start to get, difficult to follow, right? But the thing about backprop is that backprop makes this all very clean. And it also makes it all very efficient. The thing that backprop is going to do is that I'm not going to compute the derivative with respect to each of these guys separately because that would be very slow. Remember, I can have thousands or millions of weights. I'm going to use the derivatives that I computed to then compute the other derivatives as a function of those, and then this is all going to happen very fast. At least one step of this is going to be fast. It might take many steps, but that's a different problem. You had a question?
That's just to train the connection between F1 and that first hidden unit on the left?
Yeah, remember, the whole purpose of backprop is that we just want to do the same thing that we were doing before, which is to compute the gradient of the error with respect to every single one of these weights. This is what backprop is for. Backprop is for computing the gradient. And then once I have the gradient with respect to each of the weights, either at the output layer or in the hidden layer or wherever, right? Then I do the same thing as before. I multiply by the learning rate and I subtract from the weight. Okay? So everything really stays the same. It's just this critical thing of knowing how to do this across multiple layers. Does that answer your question? More questions? Okay, so let's see how we do this. So here's my sum over all the outputs. Okay? Remember, these are the units that this unit is outputting to. Okay? So this is the sum, and here's my chain rule. My chain rule is breaking this into two parts. The first part is the derivative of the final error with respect to net k. Right? This is where net k becomes important, where our delta k's are going to show up. And the second part is the derivative of net k with respect to net j. Notice in this very simple application of the chain rule is really where all the action is, right? Notice the following. So I'm now looking, going back to this diagram, right? Rachel, let me just draw it here. So here are my outputs, right? And here's my hidden unit. I have weights going into the hidden unit, right? And then I have weights going from the hidden unit to the outputs, right? K is ranging over these, okay? Summing over those, right? But what I'm trying to do is compute the derivative with respect to one of these guys, okay? I'm going to break that up into two pieces. The first piece is the derivative of the error with respect to net k, right? Net k is the unit in the next layer. I hypothetically have already done this because it's either an output unit or because I did it in a previous stage of the backprop process, okay? So this is kind of recursive in that way, right? So this guy I'm going to assume that I already have. In fact, this is what I called minus delta k. That's why, that's why the delta k's are the thing that we play with. Okay? So this guy by definition is delta k, and when I get to this point, I have already computed it, right? When I get to the point of trying to compute the derivative with respect to this guy, I'm assuming that I've already computed the derivative with respect to these guys and so forth. Okay? And then the next part, right, which is where things get more interesting, is the derivative of net k with respect to net j. Because I'm really interested in unit j at this point, right? It's just that the effect of the unit j is through the unit k, right? So this is where kind of the interesting new action is. It's the derivative of net k with respect to net j. Yeah?
What's net j again?
So net, remember, j ranges, k ranges over these guys, j ranges over these guys.
But you're only computing one of them.
No, exactly, but I'm going to show you how to do this for any one of them, and then you know how to do it for all of them.
So why is net j a component of that when...
No, so look at it this way, right? We applied the sum rule over these guys, right? But now let's look at one of those paths, right? It has a j part and it has a k part. Right?
But why is j a net when it's only one of the things that's connecting the input to the hidden unit?
No, so remember, maybe I didn't say this very clearly, right? Look back to this diagram, right? There's net. Here it wasn't indexed, right? Net is just the weighted sum of inputs at this neuron, right? And now I'm just using j and k to range over neurons, right? So, actually, maybe I know what the confusion is that we're interested in the weights, right? But these are really weights of certain units, okay? So here's my unit k, right? And here is my unit j, right? And then I'm actually, going to index over the weights going into that unit, right? So you have to keep this thing straight. There's a lot of indices, right? This is often what happens once things get, multiple layers and whatnot. There's indices over the neurons, right? And then there's indices over the inputs to the neurons, right? But you have to remember that the input to those neurons are in turn other neurons, okay? So, there's actually more than one way to do this notation, but the important thing to keep straight is that I'm interested in the variation of the error as a function of this weight. This is what I'm computing here, okay? But this weight, let me just finish, makes itself felt through this weight, okay? And so k is ranging over things in this layer, and j is ranging over things in this layer. Okay, so k is the output layer, or more generally the layer, the next layer up, and j is my current layer. Okay? You still seem a little puzzled. Why don't we go through the rest of this, and then we'll see if you still have a question. Okay? Okay, so now I'm interested in the derivative of net k with respect to net j. Right? And so now the question is, what is that? Well, if you think about this, we already saw how to do this when we were looking at doing it for a single neuron, right? This neuron happens to be inside the network instead of being at the output, but we already know how this goes, right? How does it go? D net k, D net j, in turn, can be decomposed using the chain rule into two things, right? D net k, D sigma, doj, right? This is the derivative of net k with respect to the output of my neuron in this layer, times the derivative of that output with respect to net, which is before the sigmoid, okay? This is just what we did before, except now it's for a different neuron. It's for a neuron here instead of a neuron there, okay? And now we know what these are, right? This guy is just the weight, as before, right? What weight specifically are we interested in here? Notice, this d net k doj is wkj. Wkj, this is really the important thing about the indices, right? This is what you have to have straight. It's like, wkj is the weight from unit j to unit k. Okay? So I have j here and I have k here, and I'm interested in the weight from j to k. And you see why, right? Because this guy is making itself felt through this guy, right? So I need to put that in my chain, and here it is. Okay? Everybody got this? This is a key step. Okay? And now the other part, of course, dok d net j is just my derivative of the sigmoid. Okay? Everybody with me? You might want to go through this at home, step by step, getting the indices straight and applying the chain rule and whatnot. But at this point, what you should get is the basic idea of how my derivatives get computed in a hidden layer as a function of the derivatives that I've already computed at the next layer and my sigmoids, or the derivatives of the sigmoids. Okay? Notice that what happens in general is that my network is a DAG, right? The way I handle my DAG in computing the gradient is I use the sum rule to decompose it into, and the DAG is kind of a difficult thing, right? But I use my sum rule to decompose it into separate paths, right? My error is going to be a sum over paths, right? And then each path I use the chain rule, right? So if you think about it this way, and you know how to do the differentiation for a single sigmoid unit, the rest follows. Okay? All right. So at this point we basically have what we need, right? This is my expression for the derivative with respect to net j, which is my new delta j, right? Remember, my goal is to compute my delta j because that's what I now want to use in the following layer if there is one. If there isn't one, then I just stop here. Okay? So what is this going to be? It's going to be oj times 1 minus oj, right? This comes from the sigmoid, times the sum over the outputs of delta k times wkj, which if you think about it, this is actually fairly intuitive, right? Obviously, this term is going to be there because I had to pass through a sigmoid, right? So that has to be there. And the rest is a sum, right, over the units that I'm outputting to of the corresponding weights from me to them times their errors, right? So if you actually ignore the calculus and just look at the expression that you get, it actually makes a lot of sense. If you think in terms of the chain rule and the sum rule, okay? Notice the sum rule is coming into play in the fact that I am summing over the outputs. Okay? Questions? Again, I don't expect you to have sort of like followed every step of this in 5 minutes. It's kind of not something you can do online. But hopefully you have the idea, and now you can sort of like, try doing this by yourself. Okay? And then if you have questions, you can come back to us. Okay? And then there'll be a nice little exercise to test your understanding of this in the homework. We're going to ask you to do the same thing with a slightly more complicated function, in particular a function where we've added a penalty on the weights to avoid overfitting. We're going to get to that in a little bit. Okay? Questions? This was the hardest part of today's class, and now we're over it. And you can begin that long slide into, well, no, not yet. Okay, so what's the backpropagation algorithm, right? Let's put all of this together, right? The backpropagation algorithm goes as follows. As usual, I initialize my weights to small random numbers, okay, the usual thing. And then I do the following until convergence. Notice how similar this is to the previous, just training one neuron. And then I go through each training example, right? So we're going to look at the batch version here, but again, you could do this with an incremental version or, stochastic gradient, as it's called. And then first I do a forward pass. I input my new example to the network and I compute, the values of things going forward until I have, my O value at the output, okay? And then at the output, I compute my delta k, which is just, the delta, the expression for the gradient for a single sigmoid unit, okay? And then I do this for the hidden units, right, using the expression that we just saw, right? And then finally, right, what I do is I add this up for the examples, and I do my update, okay? In incremental mode, I just do the update right after each example. In batch mode, I sum this up for all the examples. I have a big delta weight, and then I do all the deltas, all the weight updates at once. Okay, and that's backprop for you. Questions?